Cool. Thank you all for being here and sticking for the last talk of the day. And thank you very much to the organizer for organizing this beautiful conference and giving me the opportunity to present this ongoing project that I'm doing as part of my postdoc in Dr. Champalimaud. And so I'm very interested in understanding more how this optic flow processing circuits are able to have accurate representation of all the bodies moving through space. Because when you think about it, vision is very, very important for us to move through space. There's this very famous, well-known experiment where a researcher was asking participants to walk in a straight line, and what they did is to blindfold the participant. And it's really, really, really hard to walk in a straight line if you don't have visual feedback. So basically here you have 3 different participants, and you can see they were asked to do a straight walk. And it's really not great. You can see there's very curved, sometimes they start to circle. We're very, very bad at doing that. You can try yourself. If you don't believe me, you will never be able to walk straight. And fortunately for us, it's a little bit similar for flies, you will see. So a grad student at the time in the lab, Thomas Cruz, developed this assay where we have a 3D walking fly in an arena. And so the fly is here, we're tracking it right now. And we can project visual stimulus to the bottom of the arena or leave it in darkness as we want. And what we can do is to record the trajectory of the fly. And here I'm putting 2 examples, one in darkness, in the dark brown, and one in light, in a lighter brown. And the first thing that jumped to the eye is this is a very well-structured behavior for being very exploratory. The fly is doing those very structured behavior. It's forward run, then turn, then forward run, then turn. And although they're not as bad as us when walking in darkness, you can see that still, I hope you're able to see that the path in darkness is a little bit more curved. It's a little bit more difficult for them to walk in a straight line. And in fact, Thomas, at the time, came up with a metric to assess that. So he took all those forward run and looked at how much they deviate from a straight line. And he computed this way what he called a straightness index. So here in this plot, you will have in the y-axis the straightness, and in the x-axis how much visual feedback we're giving to the fly. So either darkness or dots that are bigger and bigger and bigger and providing more and more feedback. And indeed, what we can see here is that the straightness of those forward runs are increasing with the level of feedback, visual feedback we are giving to the fly. OK. And we know very well, because the fly brain is quite small, and especially the optic lobes of the fruit fly have been pretty well described, we know that there are neurons called T4, T5 that are very, very important to perceive visual motion. And indeed, if we silence those neurons, the flies are not able to walk straight, regardless of how much feedback we're giving them. And just after those T4, T5 cells, we have other very well-known canonical cells that are called LPTC, or lobule plate tangential cells. And those cells have been very well described as encoding motion of body motion of the fruit fly. So going forward, turning, rolling, pitching. And when we activate, for example, one of those LPTCs, as you can see here, when we activate on the right side, let's say one of those cells, we're able to see that the animal is turning. Regardless, we're not providing any visual information. So here we have a visual neuron. When we activate it, the fly is turning. When we silence it, the fly is turning in the other direction. But what's really, really interesting for me is this whole thing is very context dependent. So if you activate, you always have the turn. But to be able to see this left turn when silencing the right cell, you need to be in an eye forward speed condition. And it's very important to remember here that the cell is silenced exactly in the same way. So there is something going on after this cell that is triggering this different behavioral output. And for me, it's very, very interesting. And so that's why I'm really interested in understanding better how are those optic flow processing circuits, so those cells, organized in a way that is able to do course control in a very context-dependent manner. So basically, how is the brain integrating this locomotion signal, optic flow signal, like visual feedback signals, in order to output the correct behavior? And it's kind of this with this idea in mind that Mert, who was at the time also a grad student in the lab, did this gigantic, massive effort to trace using electron microscopy all of the the output of those LPTC cells. And one output in particular jumped to us as being very interesting. The bilateral inferior posterior slope, so I will say BIPS for the rest of this talk, because otherwise it's a little bit of a very long name. So the BIPS neuron is very interesting for several reasons. So for me, this way, yes. One of the major interesting facts is it receives, of course, visual information from those LPTCs, as I say, but it also receives a lot of information from ascending neurons, so from neurons that come from the ventral nerve cord, the equivalent of the spinal cord in the fly, and also a lot of central brain information. So it's kind of well placed to be doing this integration between visual information and body motion, locomotion signals. It's also, you can see here, that it's pretty well, so that's the fly brain, by the way, sorry. And here in the more popping out blue, you can see the BIPS neuron. So it's really good for me because there's only two, one per hemisphere, so it's kind of easy to track. And even more interesting, we know that BIPS play a very important role in course control. So Mert did this experiment where he put the fly in the same arena that I showed you at the beginning, where the fly is able to freely walk. And what he did, he recorded the trajectory and once again compute how much during the forward run the flies were deviating from a straight path. And what he saw is that here you have in the y-axis the angular bias, and in the x-axis the BIPS that we are silencing, so either the left BIPS, the right BIPS, or both at the same time. You can see that silencing BIPS is going to trigger a path deviation. So if we silence left, the fly tend to walk more toward left. If we silence right, they walk more toward the right. And if we silence both, well, nothing happened. So it's really kind of this neuron that is monitoring how much is going on in each side, let's say, of the body. And I should also mention that BIPS is inhibitory. It's an inhibitory neuron. So when we silence it, it releases whatever inhibition it was doing. OK, so how can we answer this question, putting BIPS in the center of all integrating optic flow and locomotion for course control? So in order to better understand what's going on, what we are doing in calcium imaging, and we are doing it most of the time in behaving animals. So as you saw this morning in the talk, very similar. We have a ball, floating ball, a fly that can walk on it. Under an objective, we have a visual display where we can or cannot project stuff depending on the experiment. And here I put you the fly line that we're using. So again, it's a GAL4. One of the big advantages of the fruit fly is that we can target very specific neuron. And here I'm expressing a G-comp, so a calcium indicator, only on the synapse of BIPS. So I'm really able to record only the output of this neuron, what it is broadcasting to the rest of the brain. OK, the first thing we need to know is how they respond only to optic flow. And those are experiments that Mert did. He removed the ball, waxed the legs to be sure that it was almost like as much only visual as possible, and he presented many different visual stimulus. I'm only presenting 3 here. So an optic flow toward the right, which corresponds to a left turn, an optic flow toward the left, which corresponds to a right turn, and an optic flow that is called progressive, that would correspond to going forward. And you can see here the z-score, so the calcium response over time for the 3 different visual stimulus, and you can see that it's responding pretty well to those rotation and to going forward, but it's also very direction specific. So this right BIPS, for example, really like turning left, or what would be the corresponding optic flow to turn left, but doesn't care at all to the opposite direction. So there is like a big direction selectivity here. OK, so now we know what the neuron care about the optic flow. But what about the locomotion? So what I did is I removed the visual stimulus, put everything in complete darkness, and the fly on the ball. So the fly is able to walk She can do whatever she wants. We are not like pushing her to do anything. It's completely kind of self-paced. And here I'm presenting an example fly, what kind of data we're able to record. So you have the forward velocity. So basically, the rotation of the ball allows us to know how the fly is walking. And we can extract the forward velocity, the angular velocity, so the turn, and the concurrent calcium signal. And I hope that you're also able to see that there's a lot going on here. And it's really not that easy to analyze this kind of data because you don't have a clear stimulus that you can say, like, oh, what is the calcium signal when this is happening? There may be only one thing that is quite easy to see, is that the calcium signals seem to rise when the fly starts to walk. So if here I pointed 3 different instances where the fly just before was completely immobile and started to walk. And I hope you're able to see that there is this increase in calcium. But in fact, what we can do is the equivalent of a stimulus-triggered average. So I'm going to take all those moments where the fly was quiescent and start to walk, and going to say that my stimulus is the initiation of a walking bout. And here on the y-axis, you have the forward velocity. On the x-axis, time, with 0 being the initiation. And the same thing for the calcium signal. And so I hope you're also able to see that there is this increase in calcium response when the fly starts to walk. And if we look at the cross covariance between the forward velocity and the calcium response, we see that there is this beautiful covariance between the 2 variables. And I don't think you can see very well, but like the 0 line would be here. So it really seems that the fly is starting to walk, and BIPS is like monitoring that. It's not BIPS that is triggering the start of the walk. So there seems to be some kind of like behavioral state response in this neuron. Okay, what about something that is linked to the turn? So here I highlighted for you a couple of peaks in the angular velocity that correspond to turns and align it with like the calcium response. And I think it's also pretty quite easy to see that there are peaks that correspond to peaks in the angular velocity. And similarly, what I can do is the same kind of stimulus-triggered average being the peak of the turn or 0 time. And this is what you see here. I separate the left turn and the right turn. So on the top, you have all the left turn, the peak center at 0. Here you have all the right turn, again, the peak center at 0, and the corresponding calcium signal. And in one direction, there is not so much happening, whereas in the other direction, we can see kind of an increase, a global increase in calcium. And okay, the data is a bit noisy, but you have to remember it's all the turn together, whatever the fly was doing before, which could matter very much. And again, if we do the cross covariance between the 2 variables, we can see like there is this positive correlation between turning in one direction, so this is only one direction, and or calcium signal. And again, the body is first, really meaning that BIPS is not triggering anything. It's more like monitoring what's going on with the fly, or is the fly moving through space. Okay, so I show you how the fly can initiate walking, what kind of the behavioral state response in BIPS. I'm showing you how it's sensitive to turn, but I don't really look at the 2 variables, the forward and the angular at the same time. So a way to do that is to do those heat map where you see in the y-axis the forward velocity, in the x-axis the angular velocity. Here I'm just plotting on one side all the preferred direction and on the other side the non-preferred direction. And it's going to be color-coded depending on the calcium signal for this beam. And so here is what it looks like. So I think it's, again, pretty obvious that there is a preferred side for this neuron, regardless of the forward velocity. But you can also kind of see this diagonal here, meaning that the neuron really like turning a lot to its preferred direction, or not turning that much, but walking very fast forward. So there is this context dependency in the way that the neuron responds. And in fact, what I can do is to take rows of this heat map and average the calcium signal across different forward velocity and plot it across the angular value, the angular velocity value. So here, for example, this line would be when it's walking very fast. This is more of a low forward speed, and this is when the fly is walking backward. And again, like the data is quite noisy, there is some overlap between the lines, but it really seems that there is this context-specific response in BIPs being like very changing, modified by how much the fly is walking forward. And it's something that we can also verify applying linear model to our data. So we take this, we apply the linear model, and we ask if OR or z-score in the model, depending on the and the forward velocity, which you can see here. So again, we have the z-score in the y-axis, the angular velocity in the x-axis, and you can see like those really separate quite well between the high, low, and backward walking. And I also want to highlight here, as in the previous slide, that it's not only a gain thing. It's not just the curve are shifting up because the animal is overall more excited. Like it's really, there's this different slope for the 3 different curves. So I think this is very, very interesting. Okay. So at the level of the locomotion, what we saw is that it's sensitive to pretty much the same cue as in the optic flow only. So sensitive to progressive and sensitive to turning. It's very direction specific in both conditions. But now we have to put the 2 conditions, those two, the optic flow and the locomotion together, to see how are BIPs combining multimodal information to really do those accurate steering control. And the way to test that is to put the fly in closed loop. So we take the angular component of the fly on the ball to close the loop to the visual display. So basically, when the fly is going to turn left, its wall is going to turn right. So it will have congruency between its motion and what it's perceiving on the screen. And I cannot yet close the loop with the forward component, but it's in the pipeline. OK, so here I'm just plotting again an example time series of what's going on for 10 seconds of closed loop, a little bit more, 20 seconds of closed loop, and 20 seconds of darkness. On the top, you have the angular velocity, so the turning, and on the bottom, you have the calcium response. And again, like when you look at this, it's not like there is an obvious difference. It's not that the calcium signal is overall way higher when it's in closed loop. But again, what we can do is to look at those cross-covariance between signals. And before that, the first thing I did is to check that there was no difference in the behavior of the fly. Because you could expect that when a fly is put in this closed loop situation, it's going to walk faster, or it's going to turn less, like many things could happen. And so here I plot for you the histogram distribution of the forward velocity on top and the angular velocity in the bottom for both closed loop and darkness. And you can see like those 2 distributions overlap completely. So at least on this very maybe crude level of analysis, it really seems that there is no obvious difference in behavior between closed loop and darkness. And yet, when we plot the cross-covariance between here you have the forward velocity, here the angular velocity. Again, closed loop is going to be this lighter blue, the darkness is dark blue, lighter red for the closed loop, darker red for the darkness. And you can see there is this sharpening of the cross-covariance between those 2 variables. So it really seems that closed loop is kind of helping the fly get a better, a more accurate representation of the way it's moving through space. OK, and yeah. So to summarize, what I show you today is that BIPs, this neuron, is very well placed to contribute to context-dependent course control because it's received many multimodal information from ascending neuron, visual projection. And it also, I should have said it, sorry, it's also a neuron that connects to premotor brain area. So it's a neuron that is also going to inform what, for example, descending neuron should send as a motor command. We know that manipulating the activity of BIPs is going to trigger a change in behavior. It's going to make the fly less able to walk straight. We see that BIPs integrate both visual feedback and self-motion in a very congruent and context-dependent manner. So it's really integrating both cue in the same way and with this very behavioral state and context-dependent manner. And finally, we saw that visual-motor interaction seems to sharpen the correlation between the neural activity and the way the fly is moving through space. So all of that tells us that it really seems BIPs is very well placed to do those visual-motor integration to inform the way the fly is moving and be able to adjust course control if, for example, it's deviating from a straight line and want to go back to where it was heading to. And with that, I will just tell you a bit about what our next steps are. So now, because again, it's the fly and we have the opportunity with the fly, what we want to do is to record from the inputs to BIPs at the same time as we're recording BIPs itself. So for example, we are going to record from ascending neurons that are providing the locomotion, potentially providing locomotion signal while we are recording from BIPs. We want also, because if you think about this as the BIPs helping an accurate representation of body motion, then I believe it has to be flexible. Because when you pick an insect in the wild, it's very rare that it has all his leg, the wing intact. Like, it's usually a little bit damaged, and it probably had to learn to readjust the way that its motion is impacting its vision. It's very much like you. If there is a lot of wind, you need to walk faster to reach the same visual feedback. So I believe that BIPs has to be flexible if it wants to have this very good representation of body motion. And again, because it's the fly, we can also put them in VR, record from the neuron, and start changing the rules of the game and change the way its motion is going to impact what it sees. And with that, I want to thank the lab, obviously Dr. Eugenia Chiappe, for allowing me to carry this project in her lab and being such a great mentor. Mertz, Mertz, we're going to leave very soon in another lab, but was very critical and developed a lot of what I'm using now for my postdoc. And Dr. Nelia Varela, who is our lab manager and is doing a lot of work to help us with our daily life with the flies, and also all the CCU platform, because they're amazing and we are very, very lucky to have them. And with that, I thank you all.